We are starting the second session, Construction and Demolition Waste Management 1. In the session chair, Dr. Elanur Adar.
Thank you so much. Good
Hocam,
afternoon.
şu an eksiklerimiz var.
Öyle mi? Okay.
Evet. Sanırım şu an katılabilecek Levent Köroğlu.
Levent Köroğlu ve Doğan Özel.
Doğan Özel,
yes.
evet.
Yes.
Ben buradayım.
Yes, Doğan Özel. Başlayalım mı?
Başlayalım.
Tamam, teşekkürler. Good afternoon, everyone. Welcome. Six presentation will make in this session. There are 15 minutes for each speaker. We are sorry, but there has been a little change in the presentation program. We hope it is not a problem for you. Dear Doğan Özel will make a first presentation. Dear Özel works in CDE Global Company. Dear Özel, can you introduce yourself before starting? Microphone is yours.
Yeah, thank you very much for
You're
this
welcome.
opportunity, first of all. And welcome everybody. I'm working as an employee for CDE Global Company, and we are bringing some C&D waste recycling solutions to the industry. And I'm a business development manager in the company and working for Saudi Arabia and Israel, Lebanon, Jordan, Egypt, and Turkey. And I want to give some brief information to you today regarding our solution offers in terms of the C&D waste stuff.
Can start
okay.
For your presentation.
Then, can I share my screen at the moment?
Yes, yes.
Okay. So. So to start with, I'm trying to present you today, starting with why do we need to recycle, and then I will try to answer how we can recycle, and we'll try to also show you some applications and solutions by CDE. Then I'll jump to the case studies, some of the case studies that has been accomplished by our company in the past, and then we can jump to the question section. So to start with, as I said, why do we need to recycle? Because there is a nice figure over here. It's showing that if Earth's history is compared to a calendar year, we modern humans have already existed only for 23 minutes and already used 33% of the Earth's natural resources in the last 0.2 seconds. That can be considered as an unfair level of consumption, and it is definitely not sustainable. So how can we turn this waste into the resource? We need to collect them in a proper way, and then we need to process them in a proper way again, and then we can serve to the industry, which is going to be the construction and building industry at the end of the day. So we need to develop a circular economy model to be able to do that, which we can collect the waste and we can process them, and these waste can be converted into the can be reused in the construction and building purposes. I want to give you some information regarding the sand consumption level of the Earth. 50 billion tons of sand is used every year. That's a very high number, but the sand is going to be can be considered as a main raw material for the construction purposes. So if we can see the projections for the 2060, it can reach up to 83 billion tons per year, which is approximately 60–70% more than the existing year at the moment. So that's a big consumption level. I also wanted to show you some photographs over here because most of you maybe in your daily life come across with these kind of piles, especially on the roads or outskirts of the cities. Usually this waste material can be considered as the soil or concretes, pebbles, or can be consisted like plastics, woods, ships, this kind of stuff. But this material is a very nice material to be used in the construction and building purposes again, after processing it in a nice and proper way. So it can be barely everything or literally everything, let's say. Again, and another number, just to show you the importance of the sand applications. Illegal sand extraction or illegal sand mining in the world is the number 3 when you consider the transnational crime list. And it is only after drug trafficking. And the worth of the market is approximately $200 billion. This graph is showing us, telling us at the moment that we have a lot to do at the moment in terms of recycling aggregates and sand at the moment, because when you see the numbers, it is not even 10%. The recycling ratio of the countries, as you can see, it is not more than 10%, and we can do something to improve this number, of course. That's a very low value at the moment. So how can we recycle? There are some unique challenges which can be considered as unique opportunities at the moment. First of all, there is a rigorous standards for the construction materials nowadays, and it is increasing day by day. Even if you are producing virgin materials from the quarries, it can be outspec. In most of the countries, there is a shortage for sand or aggregate sometimes. So the diminishing resources is going to be the next challenge. And byproducts and unusable materials is another challenge. Limited access to the water, especially for the Middle East countries, is another challenge. And remote locations is another challenge. When we say remote locations, for example, most of the ready mix or concrete being used in the cities, in the construction works ongoing in the cities, of course. But when you consider the quarries, they are usually far away from the point of consumption. And this is bringing us another concern, like the transportation cost, of course. And energy efficiency is always a concern. Like usual, there is a traditional way of processing this construction C&D waste. We call it as C&D waste. And when you use the traditional way of it, it is going to give you a low value and low standard product at the end of the day, which means you will lower the brand value of the recycled aggregate, you will lower the consumer or client perception, and you will lower the attractiveness of the recycled aggregate business. Once you start selling the low standard product to your ready mix plants, then their perception is going to be like this. They will think that the recycled aggregate cannot be used in high value or high standard ready mix applications, but that is not true. I will explain it. So this table is just showing the usual particle size distribution analysis of the C&D waste stuff. And usually this 75 micron content is approximately 20% in the total product. And this graph is explaining is a bit better. The dotted lines are showing or illustrating the maximum and minimum allowable limits for the construction material needs to be used in the ready mix applications. As you can see, our examples selected over here is out spec at the moment. To be able to get them in spec products, we need to play with the physical characteristics of the materials, like sizing, proper sizing, and proper classification methods, which needs to be done by cyclones, some CFCU technologies, or scrubbing applications. After processing it, we can get them into specs, of course. So applications and solutions. There is a nice figure over here, which I want to mention also. 75% of the concrete is being used at the moment in the world is non-structural. And most importantly, 50% of it is less than 3,500 PSI. So there is no need for a high quality virgin aggregate in these applications usually. So what can we do with the recycled aggregates? We can manufacture blocks. We can use it in concrete pads, concrete flooring applications, retaining blocks, some road base and asphalt applications, sometimes for pipe bedding applications, or as a drainage stone, of course. There is a nice example in UK, which our company has accomplished, Sheehan's plant. Sheehan's is very close to Oxford, and they are achieving at the moment 1890 PSI strength level with the recycled aggregates with CD's plant. But UK building block strength requirement is only 1,000, approximately 1,000 PSI. So they're already exceeding 80–90% of the requirement at the moment. And their block production facility follows a CE certified process. This is a nice example, just to show you a general overview of how C&D waste plant is going to be looking like. And there will be, at the beginning of the process, of course, there needs to be a scalping screen. And then we will have the core of the plant, which I call it as a core of the plant, is the log washers for the scrubbing application. Then we could have the fine material washing application. Of course, at the end of the day, we will make a separation and classification. After the separation, the wastewater management plant will take place, and the water is being used in this kind of a process is 95% recycled and reused in the same application. So this is the core of the plant, which is a log washer. We call it as AgMax. And its duty is to size and de-agglomerate the highly organic contamination or clay lumps in the product or in the raw feed. Then the attrition cells or CFCU technology can also be interpreted to the total process to get a better high quality product. CFCU technology, which is a kind of upward current water process, and it is to remove the highly lightweight plastics or organics, lightweight material usually, and then you will have a high quality product at the end. Water treatment plant helps us to recycle and reuse the total water is being used in the process, as I explained before. So there are some I want to show you some case studies, and there will be some short videos again. I may jump only one of them, but the videos is usually self-explanatory, and it will explain it itself. The Sheehan's group, as we referred in the presentation 2-3 pages back, and this is the plant. And the capacity of the plant is approximately 100 tons per hour at the moment. And they are manufacturing sand and aggregate fractions as listed over here. And there is a nice video explaining it. As I said, let's play it.
Thank you for your presentation, Anders Özel. Do you have any questions? Yeah, sorry.
Our Lunguleasa and Spirchez is not here now, so we can continue with Asan.
Hello to everyone. I can't hear your voice.
Hello.
Hello.
Yes.
Your presentation is finished?
The presentation is approximately, yes, almost finished, but there is only 1, 2, 3 case studies. That's all.
Okay, thank you.
If you want to jump to the question section, I'm okay with it. No problem.
Okay, okay.
Would you like me to play the video or not? Can you see the video when I play it?
Okay, okay. I see. I see.
Okay.
You can play.
Okay, then let me give the examples to you instead of playing the video. So on the left-hand side, this plant, this material is from America. On the left-hand side, you can see the excavation waste coming from the most of the time tunneling applications in New York. And on the right-hand side, in the middle, and on the right-hand side, you can see the products. And there is a huge difference, of course. So that's the plant, which is doing the job at the moment in New York. and they're manufacturing 270 tons per hour at the moment and producing 3 types of aggregates plus 1 grade of sand. Jumping the video again, and this is the Velde, Norway plant. This is the biggest C&D waste plant in the world, and its capacity is reaching up to 300 tons per hour. And again, manufacturing 3 types of aggregates, 4 types of aggregates, sorry, and 2 types of different sands, 2 grades of sands. So let's play this video at least, and then it will be finished, okay?
Okay, okay.
Yes, that's the end of the presentation, and I'm happy to answer all your questions over here, if you have any.
Ma'am, we can't hear you now.
Okay, so I'm saying that my presentation is over. Thank you very much, and I'm happy to answer your questions over here.
Do you have any questions? Thank you for your presentation, dear Özal. I am sorry.
No problem. Thank you very much.
Okay. Thank you. Our second presentation will make by Arul Lunguleasa. Dear Lunguleasa works as a professor at Transylvania University of Brasov, Faculty of Wood Engineering in Romania. He is interested in pellets, briquettes, composites from wood waste and other lignocellulose materials. Professor will share the the work titled 3 types of wood waste used from mechanical processing in order to obtain qualitative briquettes. Microphone is yours, dear Professor. Dear Professor, can you hear us?
Okay, unmute. It's okay. Share screen.
Yes,
share my
yes,
screen.
Yes.
Host disabled participant.
Okay. Share screen. Can you share? Okay. Okay.
Presentation.
Yes.
Just a moment, because
not problem.
Computer change. It's okay. This is my presentation. The name of the paper is 3 types. Okay. 3 types.
We don't see your presentation.
It's okay?
No, not okay. I don't see.
Why?
I don't know.
Why?
Can you try again? Professor Lunguleasa. Okay. It is opening.
Okay.
Yes, we see your computer screen.
Yes, it's okay.
Yes, okay.
I load my presentation.
Yes, okay.
It's okay? Okay.
Yes, okay.
Thank you very much.
You're welcome.
Vice President. This presentation is about 3 types of wood waste from mechanical proceeding, wood proceeding in order to obtain qualitative briquettes. I am Aurel Lunguleasa, and I write this with my colleague Cosmin Spîrchez from Transylvania University of Brașov, Romania. Okay, F5, it's okay.
Okay.
Firstly, I have an abstract about this paper. Abstract that present all the step of my research. All manufacturing process produce wastes in larger or smaller quantity. This is why the our paper intend to use 3 different type of waste from an workshop of mechanical wood proceeding in native state without other proceeding in order to obtain briquettes. All 3 types of briquette were analyzed from the point of view of their property, respectively the effective density, breakage resistance by compression, and also some characteristic of the raw material are presented. 3 types, namely wood dust, sawdust, dust, and shaving. These types of waste were characterized by the coefficient of expansion compared to the solid wood from which they come. Direct correlation were identified between the dimension of the raw material and the property of the briquette. Respectively, with the increase of the residual dimension, the density and the resistance decreased. The general conclusion of the paper is that the 3 types of wood waste can be used directly for obtaining briquettes without other proceeding. As an introduction about biomass, biomass is a renewable energy source because it never ends if the processes are sustainable. In this sense, it can be specified that in favorable conditions, a new tree will grow, other garbage will always be obtained, and the waste will be present at any raw material processing. There are 5 different types of biomass: wood and agricultural products, solid waste of garbage, landfill gas, biogas, ethanol, and biodiesel. Among these wood products, we can mention firewood, chopped wood chips, bark, sawdust, dust in native form or processed. In the same chapter, we have a balance of wood material and waste from a furniture factory. We can see that in this factory you can use spruce timber, beech timber, plywood, chipboard, veneer for exterior, veneer for interior, timber for packing, and so on. With some quantity. A part of this raw material is retained inside of the product, of furniture product, and other are in the form of remains or in the form of waste with different quantity and different small or large chops, chips, sawdust on sanding. Some reference about wood waste. With the waste was evaluated from some author, then explained that in time of wood proceeding about 7 to to 50% from wooden raw material become residue, but the cost of this waste valorization represent only up to 8% of the turnover. Another author put in discussion the environmental aspect of using of this renewable and biodegradable wooden material. They want to find some alternative source of secondary wood waste in order to use them in wood composite. Other authors use the wood waste for obtaining electricity or heat for dry lumber. This kind of waste is used simple or in cogeneration with the coal for a most attractive economical option. Other authors estimate the capacity of the wood material that can be used and start from the point that wood waste remain a heavily undervalued resource over the earth. Liquidis and Grigoriou analyzed the reuse of particle board waste from furniture and construction wooden items. They use these different four different hydrothermal treatment. Objective of this paper is to use three different waste from wood processing and use for obtaining briquettes, valuable briquettes with high quantity or high value, add value. Material and method. There were take this waste from chip in the form of chip from planing, sawdust from the wood splitting, and dust from the sanding processing. There is two kinds of species as beech and spruce waste in equal proportion respectively 50% beech and 50% spruce. In order to evaluate the raw material, their degree of expansion was used, as we see in the next slide. In order to obtain the expanding degree of the wood material, a graduated cylindrical vessel was used in which the material was arranged. 10 samples of each type of material were considered because there are many influencing factors of this coefficient. For a good expression of this value, there is density of the remaining to a constant that was considered the medium value of the wood that enter in this receipt. This constant was arithmetic mean of the density of the wood, two wood species, and was 545 kilos per cube meters. From this point of view, they expand the coefficient become a numerical constant and was determined with the following relation. The ratio between density of the waste and density of the wood that used for obtain this waste. In other aspect, we use a Goldmark machine for obtaining briquettes that have a diameter of 40 millimeters and length different with the dimension between 10 and 32 millimeters. They use the effective density, the resistance to breaking through compression of 20 samples according with some methodology for this combustible product. The sketch of this machine is presented below, and we can see two piston is an hydraulical machine, and obtain in this channel different length of the briquette. Briquettes are presented in the right photo with the material nearby. Breakage resistance or resistance to the breaking when the briquette is put between two plateau for obtained resistance. The sketch is presented in the figure number 3, and we see that the area of compression is the internal area, respectively, and multiplication between diameter and length of this briquette. Some results and some discussion about this briquette. Average value of density is 423 kilos per cubic meter in the case of planing wastes. Higher for in the case of sawdust, and 927 kilos per cubic meters in the case of the dust waste. It was observed that decreasing the size of the waste and increasing the degree of expansion led to increase of the density of these briquettes up to 28.2%. Table 2 present this density and average density, because there were used 20 samples for obtaining in this value, and mass, diameter, and length were used for obtaining this density. For understand some influence we used for the all free wastes, the density of the waste and density of the briquette, and we obtain there is an correlation between this kind of density. With increasing of the waste dimension, the density will decrease, as we can see in this figure 5. Relating to the breakage resistance of briquette by compression, these were depending on the type of the waste, being only 0.76 Newton per square millimeters in the case of the planing waste, 1.1 Newton per square millimeters in the case of circular sawdust, and higher 1.77 Newton per square millimeters in the case of the wood dust. For seeing these limitative value, we used the probability plot for each wastes, and you use a confidence interval of 95%. This it can see the standard deviation, average, the mean, and other property. Regarding to the quality of the briquette, we see that all these briquettes are good from the point of density, or from the point of resistance, and can be used in the without processing this waste. Conclusion. Concordance with the stipulated objective, it was clearly demonstrated that there is a problem of making briquette without other additional processing of the raw waste. The wood residue obtained from different technological operations of wood processing can be used directly for briquetting. The briquettes obtained on the gold mark machine of briquetting have a lower density than those made with other type of briquetting presses, with helical screw or with the crank connecting rod, but sufficient to exceed the limiting value of European norm. Density of briquette increased with the decrease of the dimension. Breaking strength or breakage strength of the briquettes increase with the decrease of the dimension. The final conclusion of this paper is we can use in the native state the free type of wastes that we use in this paper, and an additional grinding process would not increase the quality, but increase the expenses, the cost, and the benefit would be minor. Some references, and thank you for your attention.
And thank you for your presentation, sir. Do you have any questions? Thank you, Professor, again.
Thank you.
Now,
Thank you also.
thank you. Our third presenter is Cosmin Spîrchez. Are you here? Cosmin Spîrchez? Can you hear us, Spîrchez? Okay. Okay, we should move on. Other presenter. Next presenter is Muhammed Asan. Muhammed Asan works as a research assistant at the Technical University, Civil Engineering Department. He is still PhD student at Istanbul Technical University. He will share the work titled Investigation of the Strength Development of Concretes Containing Waste Glass Powder at Different Cement Replacement Ratios. Your microphone is your Mr. Asan.
Yes, I am here.
Okay, you can share.
Is my voice okay?
Yes.
Okay. Can I share my screen?
Okay. We wait.
I'm sharing. Is it good now?
Yes, good.
Okay.
You can start.
Okay. Hello to everyone. My name is Muhammed Asan. I am a research assistant at Gebze Technical University and also PhD student at Istanbul Technical University. The title of our study is Investigation of the Strength Development of Concretes Containing Waste Glass Powder at Different Cement Replacement Ratios. We made this research with Nevzat Saltaş and our professor Tayfun Altuğ Söylev at Gebze Technical University. Firstly, I'm going to start by defining the glass because the most component of this research is glass. Glass can be manufactured by melting a mixture of silica, sodium carbonate, dolomite, and limestone at high temperature up to 1600 Celsius degree. The mixture is then cooled to solidify without crystallization. The non-liquid and non-solid state makes glass to be an amorphous solid material. Because of its properties, for instance, transparency, pliability, bright surface, resistance to the abrasion, and durability, glass is a very useful material for human. If we talk about the production of glass, I'm not going to talk about the process, just talk about the needed materials and consumption of energy. For the production of 1 kilogram of glass, 1.2 to 1.7 kilogram of raw materials are needed. The required amount of raw material depends on the type of glass. The glass industry in Europe consumes 352 petajoules of energy annually, and it's equal to approximately 15 of Europe's total energy consumption. Each ton of glass produced causes 570 kilograms of carbon dioxide emissions. If we talk about the pros and cons of recycling of waste glass, theoretically glass is 100% recyclable and can be recycled endlessly without loss in quality and purity. Recycled glass can be substituted for up to 95% of raw materials. Energy costs drop about 2 to 3% for every 10% cullet in the manufacturing process. And 1 ton of carbon dioxide is reduced for every 6 tons of recycled container glass used in the manufacturing process. But recycling of waste glass has limited scope, such as some kind of glasses, such as windows, ovenware, Pyrex, etc., are manufactured through a different process. If these materials are introduced into the glass container manufacturing process, they can cause the production problems. On the other hand, furnace-ready cullet must also be free of contaminants such as metals, ceramics, gravel, stones, etc. Glass production amount and recycling rates of waste glass of various countries are shown in the table. According to the table, if you look at Turkey, 2/3 of the produced glass was recycled in Turkey in 2004. I couldn't find the newest information about the recycling rate. In USA, the United States of America, around 11.5 million tons of glass produced. This amount equals to approximately 4.2% of the total municipal waste of United States. 30% of the waste glass was recycled, but 60% was disposed via landfill. Glass production consumes raw material and energy and also causes carbon dioxide emission. Using nanocyclable glass in concrete can be more environmentally and economically beneficial. Let's talk about it. We can use waste glass in concrete in 3 types. Can be mixed in concrete for partial replacement of coarse aggregate, fine aggregate, or cement. Using waste glass for partial replacement of coarse aggregate was studied decades ago in 1970s. Even if it has some benefits such as reducing unit weight of concrete, there are some concerns about its sensitivity to alkali silica reaction. What is alkali silica reaction? Alkali silica reaction causes the cracks upon expansion. This cracks looks like honeycomb on the surface of concrete, and alkali silica reaction weakens the concrete and shortens its service life. Usually, partial use of waste glass instead of sand contributes to alkali silica reaction expansion, but alkali silica reaction expansion decreases as the content of and maximum grain size of sand decreases. But the subject of this study is using waste glass as supplementary cementitious material. At this point, it's necessary to define a term, pozzolan, because if we want to use waste glass as a supplementary cementitious material, it should cause a pozzolanic reaction. What is pozzolan? Pozzolan is the origin of this word coming from the city of Italy, and pozzolan is silicose or aluminous material which in itself possesses little or no cementitious value, but will in finely divided form and in the presence of water chemically react with calcium hydroxide to form compounds possessing hydraulic cementitious properties. To understand the pozzolanic reaction, we should first look at the hydration of the cement. During the hydration of cement, the calcium silica components react with water and produce 2 products. One of them is calcium silicate hydrate gel. This gel provides the concrete to gain hardness and gain its mechanical and durability properties. The other one is calcium hydroxide. Traditionally, it's called slaked lime. Slaked lime is not required for concrete. Even when it comes into contact with water, it dissolves and causing voids in the concrete. It shortens the service life of concrete. Pozzolans are important at this point because the silica in the pozzolans reacts with the slaked lime to form a calcium silicate hydrate gel. provides the development of mechanical and durability properties of concrete. We know that glass has high silica content, so if you use waste glass as a powder form, it can cause pozzolanic reaction in concrete. In some studies, it has been observed that glass has a pozzolanic effect on concrete, but I'm not going to talk about the other research because my time is limited. Although, on the other hand, using waste glass in concrete as a supplementary cementitious material has a lot of advantages. If glass powder shows pozzolanic activity enough, it can improve the durability properties of the concrete. On the other hand, using of glass powder as supplementary cementitious material in concrete can enable to produce cheaper concrete and have a cleaner environment. Because commonly, cement is the most expensive component of concrete. If we use waste glass with replacement material with cement, we are going to produce concrete more cheaper. And cement is the source of about 8% of the world's carbon dioxide emissions. And it means if we use waste glass in concrete as supplementary cementitious material, we will have a cleaner environment. If you talk about our study is experimental study, experimental research. I'm going to talk about our materials. We use our concretes, Sen1 41.5 R type cement and Kocaeli tap water. Our cement specific gravity is 3.19 tons per cubic meter. And we use 4 types of aggregates: natural sand, crushed stone sand, crushed stones, which one of them has 11 millimeter maximum grain size, and the other one has 22 millimeter maximum aggregate size. The specific gravity of fine aggregates is 2.65 tons per cubic meter, and for coarse aggregates, 2.67 tons per cubic meter. And we use waste glass in powder form because if you see a pozzolanic reaction in your concrete, your waste glass has a waste glass's grain size must be closer to cement grain size. Our waste glasses, 70% of our waste glasses has smaller than 50 micrometers grain size, and our waste glass powder specific gravity is 2.6 tons per cubic meter. As you see, the lightest component of our concrete is waste glass powder, except water. I'm going to talk about these results. Waste glass powder was used at 10, 20, and 30% cement replacement ratios by mass. The water cement ratio was constant in all mixtures. It was 0.55. Three cubes of 150 millimeter for compressive strength testing and 6 cylinders of 100 times 200 millimeter for splitting tensile strength testing were cast for each concrete mixtures. Demolding was performed after 48 hours, and then the specimens were subjected to moist curing in lime saturated water at 22 centigrade degrees until testing. We implemented slump test of fresh concrete to evaluate the workability of concrete and unit-wide test.
Sorry, Mr. Asan, you can pass quickly. We have not enough time. We have three presenters. Okay, sorry.
I can start with the results. Okay.
Okay, thank you.
Okay. The results showed that the slump increases significantly as a function of cement replacement ratio by the waste glass powder. Compared to the control sample, slump increased by 22. I am passing this part because I have to be fast. And the unit weight of fresh concrete is given in the table. Although the unit weight values are close to each other, it has been observed that the unit weight decreases as the amount of the waste glass increases. I have to be quick. If you look to the composite strength test result, at the end of the 7 days, the strength loss of concrete containing 10% glass powder compared to the control samples was 11%, while at the end of 91 days, the difference was reduced to 7%. The other one. The tensile strength of samples behaved similar to the compressive strength. At the end of 7 days, the tensile strength loss of concrete containing 10% glass powder compared to the control samples was 6%, while at the end of the 91 days, the difference was reduced to 2%. I am pressing this. Okay. Conclusions: using glass powder as a supplementary cementitious materials in concrete was increased the slump volume of concrete. Since the unit weight of glass powder is lower than cement, using glass powder was reduced to the unit weight of concrete. Although the compressive and tensile strength of the samples containing glass powder are lower than the control samples, the difference between them was decreased over time. Using of glass powder was delayed the concrete gaining its strength. It was observed that the number of unbroken aggregates on the fracture surface increased as the amount of glass powder increased. Finally, the results of the present study emphasized the potential of waste glass powder as a cementitious material. The cement replacement ratio of 10% seemed to be a limit value beyond which the strength reduced dramatically. On the other hand, there was a significant recovery at later rates of curing. Thank you for your attention. If you want, you can hear me via this email address.
And thank you for your presentation, dear Asan. Can you, do you have any questions? Okay.
It was really fast. I hope you, I can understand. I can explain our research.
Okay, thank you so much. Your attention. Next presenter is Spirchez. Spirchez is a lecturer university at Transylvania University of Brasov in Romania. PhD in industrial engineering since 2010. Spirchez is interested in wood processing for wood industry, devices for wood industry, wood construction, and wood biomass. Dear Spirchez will share the work titled A Comparative Study Regarding to Pellets and Briquettes Properties of Corn Cobs. Can you hear us, Spirchez? Spirchez?
Dă-drumul la cameră.
Dear Spirchez, can you hear us? Can you hear us, Spirchez? Dear Cosmin, are you here?
Să vină calculatorul dumneavoastră cu prezentarea sau?
Zi, mă, că te auzi.
Hmm?
Zic că auzi.
Hello.
Hello. You can
Now put in the presentation. Load.
Okay. Yeah, you didn't present? Dear Cosmin?
Okay. Now share your screen. Now begin.
Okay, okay. You can share screen and begin. Can you share screen, dear Cosmin?
Okay, immediately.
Okay.
The title of paper is a corn cobs. The author is Cosmin Spîrchez and my colleague Aurel Lunguleasa, Transylvania University of Brașov. Biomass is a renewable energy source by means of fact that is grow year after year. It is widely spread throughout the world and it covers low cost compared to fossil fuel. Biomass resources from which combustion material is produced can include waste resulting from the production of agriculture grains, municipal waste, and residual waste. Biomass differ from the other form of renewable energy sources via the fact that it represents a rich type of raw material that can transport it by means of various conversion process into gas or solid fuel. Waste resulting from agriculture production, from agriculture process, grain waste, and urban organic waste. The material and method presented, the actual density has been established according to standard EN 15103 in order to establish the actual density of the pellets and briquettes made from corn cobs, 20 pieces of which were taken into consideration. In order to establish the effective densities, the following relation was used, presented in figure. In order to establish the bulk density of the pellets, tape container was used having the following dimensions. The installation used for determining the caloric power of the pellets made from corn cobs was the calorimeter with explosive combustion, presented in figure 1. The net caloric power of the pellets from corn cobs is established on the basis of the formula presented. In figure 2 is presented description of the process for establishing the caloric power of pellets and briquettes made from corn cobs. The process of establishing the ash content was performed according to European standard presented. The ash content of the sample is calculated a relation. Result and discussion. The moisture content level for the pellets made from corn cobs was 9%, and for the briquettes made from corn cobs it was 10%. the value of the actual density for the 4 types of pellets and briquettes vary from 829 kilogram per meter cube to 1,255 kilogram per meter cube. In figure 3, presented the values of the effective density for the 4 type of pellets. And the figure 4 is presented the values of the bulk density for the 4 type pellets. The value of the gross caloric power vary from 19,687 kilojoule per kilogram to 19,902 kilojoule per kilogram. In figure 4, the graphic representation of the value for the high caloric power is displayed for pellets and briquettes made from corn cobs. In figure 5 is present the value for the burnt ash content for briquettes and pellets of corn cobs. In conclusion, biomass is the most widely spread resources, which includes alongside biomass, wood processing, residue, and agriculture residues. The value of the minimum actual density is for briquettes 829, maximum value of 1,255 is for the 500 type pellets. The value of the high caloric power and the low caloric power is greater case of pellets than for briquettes made from corn cobs due to the low compression. The value of the ash content for pellets made from corn cobs as well as briquettes made from corn cobs is lower than 6% according to standards. Thank you for your attention.
And thank you for your dear Spirchez. Do you have any questions? Thank you.
Thank you.
Thank you. The next presenter is Levent Köroğlu. Köroğlu will present the work titled Valorization of Heat-Treated Boron Derivative Waste with Different Particle Sizes as Portland Cement Replacements. Can you introduce yourself before starting, dear Köroğlu?
Okay, now I'm sharing the
Okay.
screen. So, okay, hello everyone. I hope you are healthy now. I'm Levent Köroğlu. I am research assistant and also the PhD student at the Department of Material Science and Engineering in Eskişehir Technical University. I work with Dr. Derya Över Kaman and Dr. Erhan Ayaz. So, as you said, we focused on the valorization of heat-treated boron derivative wastes with different particle sizes as Portland cement replacements. So, I would like to briefly mention about the strength mechanism of cement mortar. As you know, the cement mortars gain strength by the hydration of the cementitious materials. There is an interfacial transition zone between the aggregate and bulk cement paste, so that hydration, following the hydration, some hydrated products fills in this zone, and then mainly the hydration products are the calcium silicate hydrate, calcium hydrate, and etringite. Now you can see the main formation reactions for the hydration of silicates and aluminates in cement. As you see, the calcium silicate hydrate, calcium hydrate called as Portlandite, and also the etringite is formed in the structure. So what's the importance of the particle size distribution of cementitious materials? Particle size distributions have an effect on the heat evolution, microstructure, hardened characteristic of cement-based materials. So the particle size distribution controls the packing of cement particles and also affects the viscosity and strength of the cement mortars. So when the particle size of the cement decreases, we have higher diffusivity, higher rate of hydration, narrows interfacial transition zone, and also it increases the packing density. So finally we have higher strength for the cement mortars. I would like to mention about boron reserves and boron derivative waste quickly. So Turkey has 72% of boron reserves in the world wide. In Eskişehir, a city of the Turkey, in Kırka, plant of eti mine works. Approximately 900,000 tons of boron derivative waste are generated during 1 million tons of borax pentahydrate production. Borax pentahydrate is a boron mineral and came from boron mining and is used for the many industrial sectors. So the high amount of waste causes the costly waste storage and unfortunately environmental pollutions. So what's the boron derivative waste? The chemical composition of the boron derivative waste is composed of mainly silicium, calcium, magnesium, boron, sodium, and aluminum elements. And also there are also the traces elements existed in the structure. So what about the crystalline phases in waste? So according to XRD analysis, X-ray diffraction analysis, dolomite, calcium magnesium carbonate, calcite, calcium carbonate, quartz, borax pentahydrate, and kaolinite can be found in the waste. So the major phases are the dolomite, calcite, and quartz. So you can see that in here, these phases include the carbonates. So with the heat treatment, we can remove these carbonates, and then we can provide the reactions between these phases. So the aims of the study is to firstly the investigation of the effect of particle size distribution of heat-treated boron derivative waste as a Portland cement replacement by 25 weight percentage. It's a stable content on the mineralogical, microstructural, and mechanical properties of cement mortars. With the waste utilization, we can overcome the waste storage problems and also prevent environmental pollutions. So firstly, we heat-treated the boron derivative waste at 800 centigrade for 1 hour. After that, we crushed and milled the waste powders by using agate mortar and ring mill. So you can see now at the first picture, the heat-treated boron derivative waste after just obtained by heat treatment, and then the second picture shows the crushed powder, and the third one shows the ring milled powder. So you can see the decreasing of the particle size distribution. So the second, we prepared pastes. These pastes is composed of the Portland cement, heat-treated derivative waste, which have 3 different particle size distribution, and water. We kept the waste and cement ratio as stable as the 25 weight percentage, and we aged these pastes for 28 days. Thirdly, we prepared cement mortars according to the ASTM standard. We use Portland cement, heat-treated wastes, sand, and water. Again, these ratios was kept stable. We aged these cement mortars for 7 and 28 days. So the reference cement mortar didn't include the heat-treated waste, and the other waste, according to the particle size distribution, we called as the coarse, medium, and fine heat-treated wastes. So finally, we accomplished characterization, particle size analysis, phase analysis, compressive strength test, and microstructural analysis were performed using these devices. So, as you know, the Portland cement includes the calcium silicates, gypsum, calcium aluminate, and boron minerate phases. So, what's the particle size distribution of the cement and wastes? You can see in here the coarse heat-treated powder has much broadened the particle size distribution. The medium powder has equal median particle size compared to cement, but the particle size range is slightly broadened, and the fine powder has exactly the same particle size range compared to cement. So you are seeing now the XRD patterns of the ground powders. XRD patterns are the same, just a bit difference in here. So the acarmanate peak decreases with the decreasing of the particle size due to the amorphization of acarmanate phase is detected by the XRD analyzers, but all patterns are the same. So now you see the phase evolution of pestes. So on the reference pest, we observed as known phases and also the major hydration products, calcium hydrate, calcium silicate hydrate, and also a bit ethringate phase. So the heat-treated waste incorporated pestes has also the same, the similar XRD pattern, just a bit difference in here due to the phases coming from the heat-treated waste. After the heat treatment of waste, some calcium magnesium based phases and also the quarks are formed in the structure, and we observe these phases as a minor crystalline phases in the structure, but all XRD patterns the same hydration products were detected. So you can see now the comprehensive strength values for the 7th aging day and 28th aging days. So after the addition of the coarse powder, we had a quite loss in the compressive strength, but for the other medium and fine powders, we got the strength values in the acceptable strength ratio, and with the increasing of the aging time, the strength values increased a bit. And in briefly, the particle size distribution affects the strength values. It is the strength activity index. So we accept 100% for the reference cement mortar, and for coarse powder, there's a reduction of the strength, and the highest value is obtained for the medium heat treated powder. Much broader particle size range provided quite low strength, as I said before, due to the high interparticle spacing, which needs more hydration. In terms of strength values, medium and fine powder could be used in concrete applications. It's important that the heat-treated waste act as fillers, but is not reactive like cement, because with the addition of the heat-treated waste powder, we have a little bit loss in the compressive strength, even the medium for the fine powders. So with the aging time, the cement mortars has getting more compaction. I mean, with the formation of the hydrated products, it leads to higher packing density in the cement mortar. So there is an opposite relationship between the compressive strength and the length distortion. We measured the length distortion of cement mortars on z-axis after the 28 aging days. In briefly, you can see the values in here. There is an expansion occurred for the coarse powder with the much broader particle size, and for the reference mortar and medium waste incorporated waste has similar length distortion. It means the equal compaction ratio, and it shows the availability for the application. So according to literature, the morphology of calcium silicon hydrate is needle form into honeycomb structure. Portlandite formed in hexagonal plate and also in column aggregate shapes. Ethringate has thick needle shape with hexagonal cross section. So we wanted to check this formation. These are the SEM images, EDX spectrums taken by scanning electron microscope. In here, we made spot analysis on the honeycomb structure and point spot analysis on the hexagonal plate. So the obtained values shows the formation of the calcium silicate hydrate and calcium hydroxide, Portlandite, I mean, but in here we cannot measure the hydrogen elements by the EDX spectrum. That's why you cannot see this element on the list. So now you are seeing the SEM images after 7 days aging. The all cement mortars has similar, the same hydration products, and with the increasing of the aging time, the amount of the hydrated products are much more increased. But there's a difference in here. This cement mortar incorporated by the coarse powder has some much more voids in the structure. This data also supports the length distribution, length distortion data, because this cement mortar has an expansion after the 28 aging days. So as a conclusion, we investigate the effect of the particle size distribution of heat-treated boron derivative waste on the properties of cement mortars. We used as a replacement by the 25 weight percentage. We achieved heat-treated wastes with 3 different particle size distributions. According to obtained data, 94.5% of compressive strength of reference mortar was obtained with slightly broader particle size range of medium heat-treated boron derivative waste. Much more broader particle size caused the strength loss because of the lower packing density, but it should be noticed that the eco-friendly and cheaper cement mortars can be produced with the replacement of ground heat-treated wastes with cement, with the replacement of this with cement by 25 weight percentage. So thank you for your attention. I wish you all healthy days.
Thank you for your presentation, Dr. Köroğlu. Do you have any questions? Okay, this session is finished. Thank you for all presenters and participants. We wish you healthy days and we hope to see you in the face-to-face next symposiums. Thank you.
Thanks for your participations.